Sometimes it does help to review some of the basic concepts that we have covered so far. And if you have been following at the things that we have done, you will find out that we tried to review some basic algebra, the one you did at high school. And we talked about the laws of exponents, and then we also talked about laws of surds, and then we talked about rationalization, right? Whereby we're looking at the conjugate of a given surd. And then we also talked about factorization, and we emphasized that the splitting of the middle term is one splitting of the middle term method is one of the methods that are very powerful, and we used that method to actually find out the solutions of a quadratic equation. And also the completing of a square method, we said that this one actually is way more powerful. And then we talked about a long division, and we also talked about factorization by inspection. And then we said that in some cases whereby the coefficients or the constants in front of a variable are following a binomial expansion, we can also use binomial theorem to factorize. And then some of the students were asking, what if I am good with inspection? Will that be enough for the factorization that we need? And others are asking, what if I am good with long division or the synthetic method? Is that gonna be enough for me? Because sometimes I forget this binomial theorem. And then I said the binomial theorem is, when it comes to factorization, is less powerful compared to the long division and the factorization by inspection. But factorization by inspection and synthetic division, you can use either. So if inspection can be used, long division can be used. If long division can be used, inspection can be used. So if you are good to answer the question of which one is better or which one is more powerful, so if you are good with synthetic division, you don't have to worry about binomial theorem or the Pascal's triangle, and you also don't have to worry about inspection. And if you are good with inspection, you don't have to worry about long division and the binomial theorem. That's where we were dealing with this. And then we said that we can also use these factorization techniques when we are trying to find the roots of a given equation, because this is just finding the set of x values or the set of input values that are making a given expression equal to 0. So we use this to actually solve that. So that's where these things came in place. And then from there we moved, and then we talked about the number system. We talked about real numbers, we talked about rational numbers, we talked about irrational numbers, and there are other numbers in between that set. And we also mentioned that the bigger set of numbers is a complex number system, but we're only going to be studying a subset, which is the real number system. So anything that goes to imaginal values, we don't touch that. We say that's just undefined for us. And then we went to solving inequalities. And the inequalities, we said that if you want to solve inequality, first step, take everything to the left hand side, and then after you have taken everything to the left hand side, the next step is to change inequality sign to equality sign. And then from there, once you change that, you find the critical values, which is you want to find out the set of input values or the x values that are making that particular equation equal to 0. Which means if you have a fraction, the numerator, the values that are making the numerator equal to 0, and also you also want to find the values of x that are making the function the given equation undefined, or the set of input values if you have a fraction that is making the denominator equal to 0. So that's how we go with that, and then you draw a number line. From the number line you can pick the desired region. And then we came to talk about the interval notation. Interval notation was very simple, that you can either use these brackets or those brackets, or just use less than or equal to, or greater than or equal to, or less than, or that. That's what is actually in here. And in some cases you'll find out that you end up using these brackets, or use these brackets or those brackets. These ones are when you are able to list everything one by one. It's an attempt to list everything one by one. And this one, when you have a dance of numbers in between and you can't list them one by one. And also this is the same case, but this number that is here is included when you're using these brackets, and this number here is not included when you're using these brackets. And then we moved to domain calculations, and we said a domain is a set of all possible input values that make a function defined. We worked along with this, and then we talked about symmetry, even symmetry, and odd symmetry, and most importantly, you have to be able to differentiate between even symmetry and other reflections, odd symmetry and other reflections, that we'll be covering in this particular session. So after finishing these things, odd symmetry and even symmetry, we talked about power functions, we talked about polynomial functions, we talked about rational functions, we talked about algebraic functions, we talked about trigonometric functions, and I gave you a homework here and said, can you try and plot cosine of x and sec x, and then plot these two functions, and then try and plot the tangent of x and the cotangent of x. So I wanted you to plot these things. Hopefully you did try to plot this using the analysis that we used when you're plotting sine and cosecant of x. And if you haven't, I will find time tomorrow and plot this using the same analysis. But to plot a 10x is easy. Just plot cos and sine on the same set of x's, and then you keep dividing these values, you will be able to get that. And the same thing here, you can plot this by plotting sine and cos, and then you keep checking these values. That's just one shortest way to deal with the plotting of that. And then yesterday we had an attempt at talking about the exponential functions and logarithmic functions. So please do double check that lesson if you missed it, so that at least you get a little bit of understanding on exponential and logarithmic functions. So these are the things that we have covered, and as you have noticed that as you go this way along these topics that we are covering, you start to see everything that you started to see things in our prescribed textbook, and some of the things that are above there, you will find out that they are not in the textbook. The reason being, those things that are not in the textbook are the things that we're supposed to have covered when you were still in high school. So in a nutshell is, how do you end up studying now to make sure that, one, you are not left behind, and two, you are actually accessing all the material? So the first thing that you'll have to do, use the slides that are always uploaded on a weekly basis. Study everything that is there. Make sure that you understand it. If you have something that you are not sure of, go to the prescribed textbook and see if you can study that session there. And then after doing that, you are actually using your tutorials to answer a bunch of questions and see if you are actually getting them right or not. And then, of course, if you feel like you tried to solve them, you saw the solutions, but you still don't understand them, you can either ask your tutors or you can ask or book an appointment, and then that's when you'll be able to see me. Then we discuss the problem. And then regarding the other topics whereby you feel like they are not in the textbook, you don't understand the slides, and either you're not comfortable to have a consultation as yet, answer series, I do believe that it has some of these basic concepts that you were supposed to do in metric. So answer series and the prescribed textbook. If you don't have answer series, any other alternative textbook that you used, you can, I think it can be used, or you can go to the teachers center. I think they would have, I do believe that they would have a textbook that would be suitable, or the library that has grade 12, grade 11, and grade 10 topics. So that's all there is to this. Now I want us to look at shifting, scaling, and reflecting. And this one we will do it on Monday. I want us to do these three and see if we can actually get an understanding of graphing, real graphing now, not only the basic functions. So to begin with, let me just write it here. We will be dealing with elemental transformations. And under elemental transformations, we'll be talking about shifting of functions. This is shifting, scaling, or stretching. Stretching, of shifting, with scaling and stretching, and reflecting of functions. Do that. Is it there? Place it there. And then now let's start with the basic knowledge about this. The first thing I want us to think of, suppose we have a positive real constant. I'm just gonna say here positive constant c, that is, it is greater than 0. It's not equal to 0, it is greater than 0. And we have some function y is equal to f of x. Is a function. In other words, every input value, it has one output value. So we have f of x is a function. Right. So we're gonna look at one. Y is equal to f of x plus a c. Remember that our c is positive here. So the meaning of this is saying that this is just saying that we take f of x, we take this function and then we shift it c units up. So this one is y is equal to f of x shifted c units vertically upwards. Right. And then the second one, y is equal to f of x minus c, is y is equal to f of x shifted c units vertically downwards. Right. Before we proceed, let's take a simple example here. Suppose I am saying to you that I gave you this function here, and this function here is of this type here. This is going to be y, this is going to be x, and then I am saying to you that I have a function of this type here. Let me say that I have let me try like this, and this here, this point here is c, it's minus c, and then this point there is c. So if I move this graph here by c units, this point will be here, so we'll end up having something of this kind. And then this one here will be 2 times c, because it's gonna move c units up. I'm moving it c units up. So this is going to be, if this one was y is equal to f of x, this one is going to be this one here. This function here is going to be y is equal to f of c, f of x plus some c. So I've shifted this curve by c units. I've pushed this curve up by c units. Let me try a different example. Maybe that one will be much more clear. So this one I have y, here I have x. So if I have this function here, and I'm gonna have this function here, let's say this is y is equal to x squared. Now I want to find out where will my y is equal to x squared plus a 2, and I also want to find out where will be my y is equal to x squared minus a 2. So having a 2 is positive, and we are having a positive here. This graph here is saying I want to shift this whole curve by 2 units up. So I want to lift it. Here is 0. If you want to shift a 0 to 2, you're gonna have to move 1, 2, so we're gonna be there. And then all the other points will be pushed up. So this curve here will look something like this. And then this side here is gonna look something like that. This curve is going to be y is equal to x squared plus 2. Again, we're shifting everything up, so we're shifting this by 2 units. Okay. Now, this curve here is saying that I want you to take this function here, f of x is equal to x squared, and then you would shift it 2 units down. So this one, I wanted to move this point here. I want it to be where's this? Let me use a blue. This one I want it to be blue because it's different. It's gonna be blue. So I want to move this 2 units down. 0, 1, 2. I want it to move down there, and everything of this green curve here I wanted to move by 2 units. So we're gonna have something of this type here. So this one is y is equal to x squared minus a 2. So you move the whole curve up by 2 units to get this curve from this curve. And for this one here, you move the whole curve down by 2 units. And if you note into this thing here, shifting 2 units means moving it up. Shifting 2 units down, it means you are actually moving the curve down by 2 units. Now, what else there is to this thing? Let's look at number 3 now. If I want you to find y is equal to let me say now I have f of x minus c, and then this one here I want y is equal to f of x plus c. This one here is saying is y is equal to f of x shifted c units to the right. And then this one here is saying y is equal to f of x shifted c units to the left. So I want you to take a note of this. We have a minus, but we're moving to the right. And here we have a plus, and we're moving to the left. That's what is important. I want you to notice here. And here we have plus, and plus is going up, and we have minus, minus is going down. So there is that difference here. Don't make a mistake. Make sure that you get these things right here. So an example will be, this is an example. We have an example here. An example would be, I have this nice function here. Let me do this. I have this nice function. Here. And of course, this is y and this one is x. And I am saying that I'm still gonna use the same curve for this particular example here. I have this curve here, and this is y is equal to x squared. And then now I want us to find y is equal to x minus 1 squared, and also I want us to find y is equal to x plus 1 squared. Now, if let's say we want to find out this, if you look in rule 3 is saying that when you have a minus there, you're moving to the right. So you pick a point here which is 0, and you want to move it 1 unit to the right, so that point should be there. You pick this point there, you wanted to move it by 1 unit to the right, is supposed to be there. You pick a point on the curve and you want to move it 1 unit, it should be there. So you're actually moving this to the right. So you're gonna have a nice curve that is of this type here. It has to pass this point, pass that point, and then it goes up. So you're pushing this curve a little bit to the right, or you are shifting it to the right. Note that here, when you have something of this type or that type, you are moving the whole curve. So the whole curve is moved. So this one here is y is equal to x is equal to minus 1. And in this one here, every point in the original equation, you move it 1 unit to the left. This point here, I wanted to move it there. This point here, I wanted to move it to the left. So the new curve that we'll have is gonna pass through this y is equal to x squared. So we're gonna have our x plus a 1 squared, and then here this one is gonna go this way. Of course, you can see that now this curve was moved to the left and this curve was moved to the left. That's the meaning of these two rules here. And now let's look at the other remaining rules here. So let me go back to black. We are supposed to be, I think we're at 5 now. If I'm saying y is equal to c times f of x, what is the meaning of that? And then also I want us, let me place this one here. Y is equal to f of c of x. And then what is the meaning of that? And of course I'm gonna have let me first deal with that and make an example, and then come to this and make an example. Let me cancel this one out so that we don't end up confusing these two. This one is saying that let me write this. This is saying I have y is equal to f of x originally, and this function here is scaled, or let me use the word stretched. The spelling is supposed to have a T, is stretched vertically. Stretched vertically by a factor c. So this function here is scaled vertically by a factor c. So that we have this. There are few points that I would like us to note here. Most students they usually struggle with this because they don't really know the difference of stretching. When you are stretching a function, the solutions of that function, the solutions or the x-intercepts of that function are locked. In other words, they don't change. The only thing that will change is all the other points. Let me just say here, but all the other points are moved. Right. So when you're stretching something, if something was above the x-axis, then it is moved up. Let me write this thing here. If something, or let me not just say something, the curve is above the x-axis, and c is greater than 1, the curve will move up. Remember that the x-intercepts are locked there, and if c is greater than 1, the curve will move up. All the other parts that are above the axis will move up. All the curve, okay, if something is above the x-axis, it will move up. That's what I was trying to say here. And then secondly, if the curve, let me just say the curve portion instead of this. If the curve portion is above the x-axis and c is between 0 and 1, then the curve portion moves a little bit down. It's gonna move a little bit down. And the opposite of this, if the curve is below the axis and c is greater than 1, the curve will move down even further. That's what is actually happening here. And of course the same thing will happen here. It will get closer to the x-axis. Let us try and take an example of this. I want us to see if we can actually get an example of this. I am going to say that we have, this is our example. I want us to say y is equal to x squared. We're going to have that. And then I want us to take questions on y is going to be equal to 2 times x squared. And then I want us to have y is equal to 1. No. We have 2x squared. I want us to have y is equal to 0.5x squared. And then I want us to have y is equal to 0.25x squared. Those are the examples that we'll take a look at. Now, I want you to also notice that we have this constant here, we have this constant here, and then we also have that constant there. And we can also have a last one here and say we have y is equal to 3x squared. And then I also want you to take a note of a 3 there. Now, to draw these functions here, or this elemental transformation of this particular function here, first we need to draw this function here. So we're gonna have our nice ruler. I'm gonna place a nice ruler somewhere there. I'm gonna place a ruler there. Let's move down. So we're gonna have this, and of course we're gonna move to this side here. Now we plot this curve here. We know that y is equal to x squared looks like this. I'm trying to make it as big as we can here so that we can clearly see what's going to happen. This is y is equal to x squared. Now, let's go to this one here. First, I'm going to use a blue. Okay, this one is going to be blue. And then this one, I'm going to make it a green. And then this one here, I'm going to make it, I want to make this one red. And then this one here, I want to make it orange, the last one. And then we'll look at the difference here. Rule number 1, when you're plotting this, we're starting with the blue. This point here, because it is the x intercept, when y is equal to 0, x is equal to 0, right? When x is equal to 0, y is equal to 0. So this is the x intercept here. Now that we have this x intercept, what I want you to take note of is this. This point here is locked, it's not going anywhere. So this one is fixed, or you can say fixed or locked, so it's not going anywhere when we are dealing with these things here. But now we have 2, we have a 1 there. So this 2 here is bigger than a 1. So because this 1 is bigger, this 2 is bigger than 1, which means that we're gonna be stretching this thing up. So when you're holding this thing and you are stretching it, it's supposed to move a little bit up. And every single point will be moving a little bit up. And everything here will be moving a little bit up. So that is what you are actually doing. So the new curve will be going somewhere like this. And then it's going to be going somewhere like this. Because you have stressed every point, so this point here is not locked anywhere, so it's gonna move up. But this one here is locked with a nail, so it's not going anywhere. So this one is y is equal to 2x squared. And let's plot this last one here. If you look into this one, this 3 is bigger than 2, which means the strength of pulling this this function here is bigger than the strength that was used here, which means this one will also be above there. But I want you to take a note that this point here is locked with the nail, it's not going anywhere. So this new curve will be going like this, and then it should be a nice curve like this. So this is y is equal to 3x squared. So we are locking this point here, it's not going anywhere, so it's just sitting there. And then let's also look at, now this one is done, this one is done. Let's look at 0,5. If you look at this strength here, it is less than that one, and at the same time it is less than a 1. What does this simply mean is that we are not really going to stretch this function now, we are going to shrink it a little bit. So when you're shrinking a function by this half here, between this point and that point we are going to about half. So this one here, we said we're gonna use green. So between this point and that point, this function will go to about half. It's gonna go that way. So we're gonna have y is equal to 0,5 x squared. So that's what is actually happening here, because this is less than 1. So if it is less than 1, it's gonna be below the previous, the original function, because looking at 0,5, the strength of this is less than the strength of that. So to get this function from that function, we need to pull this one a little bit up. So this one will be below. So that's the meaning of these numbers there. And also this side here, of course, this point is always going to be locked because it is the x-intercept or the solution of that. Or you can think of it as if there is a nail there. There is a nail there that has been placed so that it keeps this. So you can pull this as much as you want to pull it. And then this one is done also. And also if you look at this one, the strength of pulling is less than the strength of pulling this one upwards. So this one will be below. So we're gonna use a red one here. So it will be, of course, this point will be locked there. So it's gonna be below just like that. So it's gonna be going a little bit below like this. So this is y is equal to 0,25 x squared. So this is how you plot these nice functions there. Now let us look at a different case. I think this one will be much more interesting. Let's take another example here, the one that will have so many x-intercepts. So I'm going to say here we're gonna have our original y is going to be our sine of x. And I want us to visualize and plot y is equal to 2 sine of x. Okay. Let me do this instead. Y is equal to 0,25 sine of x. And then I want us to look at y is equal to 0,5 sine of x. And then I have y is equal to 2 sine of x, and then I can maybe say y is equal to 3 sine of x. Now, how do we end up dealing with that nice illustration there? Let us take a look into this. So we're gonna have, let me place a ruler somewhere. So you're gonna have this, and then this side you're gonna have a nice curve. Now when we are dealing with this, you will find out that you have some interesting points there, and then this side, let me just place a 1 will be there. This is going to be our 1, this is going to be -1. And then I'm just gonna draw this and then place the points later. So this one, I am going to say that this is 1. Let me also place a 2 there and a 3 there. -2 and a -3 there. And then this is going to be x in radians, this is going to be y. And then once you have that, we have seen that sine passes through the origin, so it's going to be a smooth curve like that, and then it comes here nicely, and then it ends up there. And at this point here, you have pi over 2 or 90 degrees. You have 0 there, and at that point you have pi, and then at that point you have 2 pi, and then at that point, what do we have? So it's going to be this times 3, so it's going to be this times 2 is that, this times 3, so it's going to be 3 pi over 2. So we have this nice thing here. And this side, we're gonna also have the very same nice thing here. And then it's gonna go all the way up, and then it comes down here. Just wanted to have a very complete thing here. Of course, in this point here, you're gonna have pi over 2 minus pi here, minus 3 pi over 2, and then you have minus 2 pi there. This one is 1, this is 2, this is 3. This one is minus 1, this is minus 2, this is minus 3. Okay. Now, let us look into this curve here. I want this one to be red. So this one, I'm going to use a red for it. And then this one here, I'm going to use a green. And then this one here, I'm going to use this color here, nice color there. And then the last one, I'm going to use an orange so that we can differentiate. So let's begin with this below here. This one is y is equal to sine of x. Okay, let me make it very far so that it does not mess up what we are doing here. This one is y is equal to sine of x. Now, I said that the x-intercepts here are locked, so they are not going anywhere. So I'm going to start with that there. So I am here with the red. This point here, that point there, and that point, and that point, they are fixed there. They are not going anywhere. And then when you look into this number here, it's going to tell you from this one. If you look into 0.25, it's a quarter of that, which means that I want to make sure that this function is stressed by 0.5. In other words, I want it to be shrinked by 4. In other words, I want to shrink this by 4 because this is a quarter. So I want to shrink it by, I would say that I'm shrinking it by 4 because a fraction of a 1 is saying that I'm shrinking this curve. So this particular curve here is going to go to about a quarter there. And then this side here, I am also doing the same thing. I'm shrinking it to about a quarter there. And then, of course, I'm going to have something that is going like this. Something that is going like that. And then, of course, this side, I'm shrinking it to about a quarter and shrinking it to about a quarter. So you're going to have like that. So you can say that it's either you can say that I've scaled this by 0.25 or I have stressed it by 0.25 vertically upwards, but by the points are locked. So this one is less than 1, so the strength of pulling this up for this one is less than this the strength of this one. So this one has to be less. So you're gonna end up having a nice thing of this kind. In other words, I'm taking a quarter of this function. And then this one here is the half of this function, but it's bigger than that. So we're gonna use this one here. Note that the x-intercepts are going to be locked. They are not going anywhere. So these are not going anywhere. But the y ones, they are allowed to be moved. So I want half of the original function. So half of it is going to be somewhere there. Half of it is going to be somewhere here. Because this one, because the value is less than 1, so we are shrinking this to about half. Excuse me. And this one was shrinking it to about half. We're shrinking this to about half. we're shrinking this to about half. So we're gonna end up having a nice curve like this, and then we're gonna go all this way, gonna go up, we're gonna come down, and then we're gonna go there. Of course, this one there is going to be y is equal to 0.5 sine of x. And then if you look at 2 now, which is this nice color there, the points are still locked, they are not going anywhere. I've placed a nail there, so these points are not going anywhere. But now this function here, looking at this strength, the strength is bigger than 1 because you have a 1 there. So this means I am pulling this function with some strength such that it goes up a little bit. So I wanted to have this function such that its output is 2 times the output of that. Here, these values were less than 1, so we're shrinking this function to about half of the output. Now, we wanted to actually have pull this one with a greater strength than 1 to about 2 times the output. So these points are locked, but this point will move here 2 times 1 because this is 1. And then this one is locked, and this one is going to be going a little bit down to the negative side, and this one will be going a little bit to the negative side at -2. This one will be going a little bit up. So now our function will look like this. It's going to come here, it's going to go down, it's going to go up, it's going to come down, it's going to go down, and then it's going to come up. And of course, this one here is the one that we're gonna call y is equal to 2 sine of x. And if you look into this one, which we're gonna draw with an orange there, we're gonna have y is equal to 3 sine of x. In other words, the strength here is greater than the strength there, which means we're gonna pull this original function by a factor of 3. In other words, with scaling it by 3, we are making sure that this curve here is pulled in such a way that I get 3 times the original function. In other words, I'm pulling it, but here is the thing. This point here is not going anywhere, this point here is not going anywhere, and this point is not going anywhere. But these new points, this one I want to get 3 times, 3 times, 3 times. So this one is going to 3, this one is going to -3, and this one is going to 3, and then this one is going to -3, and then this one is locked there. If you notice, this point is pulled here this side, and that point is pulled that side, or let me just say that one, and here is pulled this way, and this one is pulled downwards. What I was trying to say here, as we are starting to have the constants that are bigger than 1, whenever you have a portion that is above the x-axis, it is pulled up. Whenever you have a portion that is down the axis, it is pulled down. This one is above, this one is above, it is pulled up. This one is above, is below, it is pulled down. That's what I was trying to say in the previous statement. So we're supposed to have a nice curve that is going through the fixed points and is going up, and then it's gonna come down, and then it's gonna go up. Of course, this one here is the one that we call y is equal to 3 sine of x. So that's basically how you plot these nice curves there. So it's just a way of pulling and pushing. So let us take a closer look now at the other portion here, which is this one is supposed to use a black. So we're gonna have I think we're supposed to be at 6. Oh, we're at 5 now. We dealt about stretching vertically by factor C. So we're stretching if the value is bigger than 1, and we are shrinking that function if the value is less than 1. We shrink it by a factor 1 over the given value. That's what is basically happening. Let me go back a little bit here. If you look into this one is stretching this curve by this factor. In other words, it is shrinking it by 1 over 0.25, which is the same as 4. So we are shrinking this original curve by 4. So you are shrinking it by 4, or you are stretching it by that factor. We are stretching this original curve by this factor, and we are shrinking it by 1 over 0.5, which is just equal to 2. So we're shrinking it by 2. The same thing here, we're stretching this by this factor 2, and we're shrinking it by 1 over a 2. So that's the difference between shrinking and stretching. And now we are trying to do an opposite here. You have your y is equal to f of cx. Last time we had y is equal to c of f of x. Now we have this. This one is y is equal to f of x, right? And this one is scaled or stretched horizontally by a factor 1 over c. This one here was scaled vertically or stretched vertically by a factor c, right? This one is stretched or scaled horizontal by a factor 1 over c. Stretched by that factor 1 over a c. In other words, this one, it is shrinked by a factor c. This one is stretched by a factor c. This one is shrinked horizontally by a factor c. So those are the differences that I want you to take a look at. Now, let us look at some of the examples of actually this, because once we get to see the examples, it's going to be easy to find out what is basically happening here. I'm gonna try and write a simple example. So I'm gonna have an example here. We're gonna have this, and then please take note of what's gonna happen here. Let me first draw this and then we explain. I've just drawn the Cartesian plane here, and then I want us to look at y is equal to x squared, y is equal to this one here is that, and then here I'm going to say I want you to plot y is equal to 2x squared. This is not 2x squared. 2x squared, and then y is equal to 3x to the power 2, and then this side I also want you to have y is equal to 0.5 x whole squared, and then I have y is equal to 0.25 x all squared. We talked about stretching, right? We talked about stretching, and first I would like us to draw the original function, which is this one, with a black pen here. Let's draw this one here. Now, what will be different here, because if you look at these numbers here, because we're here, when we're dealing with this, the x-intercepts were locked. The y-intercept, were allowed to move them anyhow. The y-intercept, they were not a problem. It's only the x-intercepts that were locked because we're pulling both vertical. Think of this having your t-shirt, and you're pulling that side and you're pulling that side. Here you have nails. There's a nail, there's a nail, there's a nail. So everything that is above the axis was moving that way, and everything was moving that way as long as C was greater than 1. And if C was less than 1, in between 0, C was in between 0 and 1, we knew that, okay, this one is going to shrink a little bit, this one is going to shrink a little bit, but these points are locked there. So we're locking the x-intercepts. In this case, we're gonna lock the y-intercepts. And if you look into this, this is a y-intercept. Of course, this is y is equal to x squared. So this will point here because it is both the x-intercept and the y-intercept. So it's going to be locked there. So now, let's look into this. I am going to make sure that at least in this particular way, we can actually plot this nicely. And also we are stretching this by a factor 1 over a c. So it's 1 over a c. That's how we are stretching this thing. I want us to focus on the stretching, leave the shrinking, because the shrinking is the opposite of this, of the stretching. So shrinking will be the opposite of this factor there. Now, what is basically happening here? We have this whole function here, and then I want us to start somewhere there, and then we go all the way down. Okay, this one will be blue, this one will be red, this one, the green, this one will be green. I want it to be green as it is, and this nice color here is coming here. Okay, now let's start here with the blue. If you look into this number here, you have 0.25. So I want to find 1 over 0.25. So 1 over 0.5, how many 0.5 are in 1? We have 4 of them. So we have this value there. Now, I am going to say this point here because it is a y-intercept, so it's locked there. And then I'm gonna pick a point there, right? And then I'm gonna stretch it by a factor 4, which is greater than 1. So if the factor is greater than 1, which means we are moving to the right, right? We're moving to the right. So I'm gonna have, if this point here, let's say maybe we're about 1, I would want to move to some point there, but this one is locked, and then this is everything that is along the y-axis is locked, but this point here, that is this point, it will be pulled to this side. So we have something of this nature here. This is your t-shirt, but here we have nails, and then we're pulling that way and that way if c is greater than, if 1 over c is greater than 1. But if 1 over c is less than 1, we are shrinking it towards this on both sides by that factor there. Okay, now this one is bigger than 1, so we are moving that way. So we're gonna have a nice curve that is way too going that way. And also here is gonna come all this way there, down there. This point is moved there, so we're gonna have this one. We said it is y is equal to 0.25 x to the power squared. And then we are done with that. Let's go to red then. Looking at red, you wanted to find out what is 1 over c. 1 over c is the same as 1 over 0.5. How many halves are in 1 is supposed to have 2 halves. So this point is locked, and we have this factor here, which is 1 over c. It is 2. So here this point is locked, and this value is greater than 1. So we are going to the right. We are stretching like this because the value is greater than 1. So we are stretching this. But now The strength of this, yes, this is bigger than 1, so it's going to be somewhere there, and it's also less than 4, which means it's going to be in between there. So this curve here is going to go somewhere in between. So this is y is equal to 0.5 x whole squared. So this is 0.5 x whole squared. And then we're done with that. Now it's time for us to go to 2 times. You wanted to find out what is 1 over c, which is 1 over, our c in this case is 2, so we have a 2. 1 over 2 is 0.5, or is half, which is less than 1. So because this is less than 1, we are shrinking this curve by half. We're shrinking this curve here by half. So we are really shrinking this curve to about half, not by half, because this is the factor we're scaling with. Yes, so we're shrinking it to about half. So this one here will actually be going, this point will be moving this way up to about half, because it is 1. So we're gonna have this, and then it's gonna pass nicely there, and this one is y is equal to 2x squared. And then this side here, wait, what did I do? Oh, I didn't complete this because it was supposed to come here. Okay, and of course we're going that side, and now we're completing this one here. It's gonna go like this. Of course this point is locked there, so we have that. And of course for this one we're gonna have, and of course for this one we're gonna end up having a nice curve that is going to pass through that point, this one here. So that's how you end up drawing this particular curve here. And another thing that you can think of, let's look at the sine function here, just as another example. Just a sine function. Maybe we can try a cosine function. I think that will be also great. I'm just gonna try a cosine function here. So what we are actually doing here, we wanted to have, this is going to be 1, 2, 3, 1, 2, 3, and then of course we have a sine function is going to start there. It's always going this way. What am I doing now? Let me move this out. So a cosine function is going to move like this, and then we're gonna work on it until we can find out what's gonna happen, and then we're gonna go all this way, and then we're gonna go there. So if this one here is y is equal to cosine of x, and now I want to find out y is equal to cosine of 2,5 0.25. I'm just gonna plot 2 here as 0.25 x, and then y is going to be equal to 0.5 x, and then here I'm gonna say I want to find cosine of 2x. I'm just gonna plot these two and then see what's gonna happen. This one is going to be blue, and this one I want to make it a red. Let's start with this one here, which is a blue. What we said here is that because we are dealing with the x-axis here, this point here, which is the y-intercept, it is going to be locked there. It's not going anywhere. And here, if you look into this here, which is 1, this point as it is, that point as it is, that point as it is. Okay, I can even continue this like this, so that you can get a full visualization of what is going on here. Yeah, so this point here, that point there, they can move, but they will move horizontally because we are going that way or that way. So we are not actually moving up and down. So this point is not supposed to go down or up, it's just moving like this. Now, what is going to happen now? all you have to notice here is that I'm gonna start with a blow here. This point here will be locked, but this point that is here, this one, I am going to move it. Let me look into this. What is 1 over 0.5? Because we are here. 1 over 0.5 is 2, right? If this 1 over 0.5 is 2, 2 is greater than 1, so we are moving to the right here. So this point here, let me do this. We are moving that way for blue. So this point here will move about, let's say, a half. I'm gonna try and make sure that I do this in a very good and clear way, so you have this, yeah. And then of course we're gonna have some nice points there. So what is this happening? So I am going to stretch this function by about 2. So whatever this value was, I'm going to multiply it by 2. This is pi over 2, and then this one is, this is 0, pi over 2, and then here this is supposed to be, okay, a cosine of 0 is 1, and then cosine of pi over 2, it is 0, and then cosine of pi is supposed to be minus 1, and then cosine of 3 pi over 2 is supposed to be 0, and then cosine of 2 pi is supposed to be 1 again. So 1, 0, minus 1, 0, because it's oscillating like that. So we have 0, we have this. At this point here, we're supposed to have a pi, and then whereby we have a minus 1, and then at this point here, whereby we have a 0, this is supposed to be 3 pi over 2. Is supposed to be like that, 3 pi over 2, and then 1 will actually be repeating that point there. And also this side here would be doing the same thing. You can see that this was supposed to continue like this, so that here we have a 2 pi, and also this one here was supposed to be something of this kind, because here we're going to have minus pi over 2, and then here we're supposed to have minus pi, and here minus 3 pi over 2, and then somewhere there we're supposed to have a minus 2 pi. Fine. Minus 2 pi. Yes, same there. Now we have a 2 that is greater than 0 there, which means that I wanted to pull this curve, push this curve here by 2 times, pull it by 2 times, such that 2 times of this become this point here. So this point, we're going to have a new point. The new point is going to be this one. So this point will be there, and this point here will be pushed by 2. I multiply this by 2, is going to be there, because I'm multiplying this is going to be 2 pi, so I'm there. And then so what's going to happen here is that this curve is going to come there, and then it becomes 0 there, and then it goes all the way up here, and then it becomes, okay, making a huge mistake here. This point is pushed there, this point here is pushed there, because 2 times pi is there. So this is where we're gonna arrive to this, and then this at some point there is gonna be pushed there, so we are going to be getting something of this kind here. That's what will happen in this time frame, because this is pushed, this one is pushed there, this one will be pushed somewhere there, because 2 times this is going to be pi. And then the same thing will happen this side, because we're gonna go all this way up there, and then we have started to go like this, and then we start to go slower. So this one is supposed to be y is equal to cosine of 0,5x. And if we go to this last one here, so we're gonna have 1 over 2, and this is less than 1. So we are pushing this curve that way for this one, because this is less than 1. So we're shrinking it a little bit, so about half. So this point, half of it will be somewhere there. This one is locked there, it's not going anywhere. And this point here is moved there, and then this one here is going to move here, and this point here is going to move to about half, and then it's gonna be somewhere there. So I have a point there, I have a point here, I have a point there, which is that, and this point will be somewhere there. So I will end up having and also this one here, because we're going this way, is gonna be there, and then this one will come down here, and then this one will be there, and then this one will be there, and then this one will be here. So I will end up having a nice curve of this type here. This is how this thing will look like. Now, if you notice here we had this whole thing here, it was kind of completed there, but here we moved, and then we completed and got some piece there. So that's how we end up plotting these nice things here. I've tried to plot them as much as I can, and hopefully we'll be able to see what is the picture of this nice thing here. And now that we have tried to plot this, of course, this one here is cosine of 2x. So we're moving this a little bit to half, and moving this a little bit half, moving this a little bit to half. So that's basically what is happening here. So the frequency, of course, it changes depending on this. Right. Now that we have talked about that one, I want us to talk about 2 things, and then we can add 1 or 2 things, and then we can say this lesson is complete. So here we have number 7, and our number 7 is just simply as, what is the meaning of y is equal to minus f of x? This is where most students usually make a mistake of confusing this with symmetry and other things, but we'll talk about it. This one is just saying that this is the original function y is equal to f of x, and it is, remember that we had y f of x. If f of x is positive, this will say that I want the negative of that. So everything that was above is going to go below, and everything that was below is going to go up. That's the meaning of this. So this is just saying f of x is reflected in the x-axis. So what was positive becomes negative, and what was negative becomes positive. Just to give you a quick example here, if you have a graph like this, and you want, this is y is equal to x squared, and then you want to find y is equal to minus x squared, all you just need to do, you place your mirror here, and then when you stand here, this will start to look like this in the mirror. So this is going to be y is equal to minus x squared. And of course, that's how this thing is all about. And then the next one, which is this, note that this is not saying that this function is an odd function. This is not, this function here is not an odd function. just because of that. So let's try and not confuse these two things, because an odd function, it has a mirror along the y-axis and a mirror along the x-axis. So at number 8, y is equal to f of minus x. This one is saying that y is equal to f of x, which is our original function, is reflected in the y-axis. So it is reflected in the y-axis. So that's what the meaning of this. So if, let's say, I'm saying you have y is equal to x squared, I'm just going to use the same example here. So you have that, and then you're going to have nice thing here, and this is y is equal to x squared, and I want you to find y is equal to minus x squared. I want to reflect this along the y-axis, so the mirror is here. So if you look into this one here, when I place a mirror here, this whole portion here, when I'm looking in the mirror, I will get this part here. And then when I'm looking at the left hand side and I'm looking into the mirror, I will get that. So this green and black are the same. In other words, this function is even. It has even symmetry, because the refraction along the y-axis give you the same thing. So that was the meaning of the even function. So this one is saying f of x is reflected by the y-axis, and then of course I can give you a different example. Like you have an example like this, and I'm saying this is y is equal to x. I want you to find y is equal to minus x. Of course, this is the same as just minus x. So this is a reflection along the y-axis. This piece this side will be going that way, and this piece this side will go that way. So this is y is equal to minus x. So these are the nice examples. And another way to look into this, you might think of this as how can I say this? Can I get maybe an example? Let me think of an example here. If, let's say, I am giving you a function and I'm saying plot, let me just say an example here. Plot f of x is equal to minus 2 x minus 1 squared minus 2 without the use of a calculator. How do you do this? This is very simple. You rewrite this in such a way that you can see all these transformations that you have been doing. The first thing here will be, I want to factor out here. I want to factor out a minus. Let me say I want to factor out here a minus here. I will have a minus, and then I will leave a 2, and then I'll have an x minus 1 squared plus a 2. How do I plot that? This is not going to be hard at all, because you're going to place your vertical axis here, and then this side you're going to have y, this side you're going to have an x. And then once you have these two things, what do you do? Okay, first look for the inner side function here. You can see that you have x squared, you have 2x minus 1 squared plus x. Forget about that, plot x squared. And x squared, you know that x squared looks like this. This is y is equal to x squared. And then what is x minus 1 squared? This is shifting this curve 1 unit to the right, so I'm gonna get a new curve now. Remember that when you're shifting, you shift everything. You don't care about the intercept or anything. So this is y is equal to x minus 1 squared. So you have this, you are done with that part. And now you have a 2 here, which means I want to scale this thing vertically upwards, because 2 is greater than a 1. So when you have this 2 here vertically upwards, it means that the x-intercepts, you lock it there. And then once you lock it, every single point is moving up. Every single point is moving up. So you will end up having a nice curve. We're not done yet. We're gonna have let me use this different color here. You're gonna have a nice curve that will come to this point, and then it's gonna come somewhere like this. And of course, this is y is equal to 2x minus 1 squared. So you have that. Now I wanted to shift this thing 2 units up. So this was 1, this was 2. So I want to start somewhere here. And then this one, let me make it a blue. So this one is going to be like this. Note that when you are shifting something, you shift everything. So because of these two, we shift it 2 units up. And now that we have done this, we have done this part. So this function here is 2x minus 1 squared plus a 2, shifting this thing 2 units up. And then once you have shifted it 2 units up, you have a minus. A minus is very simply saying that what was up, it needs to go down. So we're just reflecting this function across the x-axis, or you have a mirror there. So if you look into this, the mirror looking into this, you will end up having a function like this. This is 2, so it's gonna go to minus, where is minus 2? Or this one is going to be minus 2, something like this. This is bad, but it's looking a little bit better. So it's gonna look something of this kind. That's how you end up combining these things. And of course, this one is the original function, which is f of x is equal to minus 2x minus 1 squared plus a 2, which is the same as minus 2x minus 1 squared minus a 2. So this is the final image that we're looking for. Yes, this is how you combine everything, but you go, as we were saying here, that you look at this vector if you are dealing with something that is inside with an x. So you are looking at the horizontal axis, and if it's something outside, you are looking with the vertical axis. That's what you do. Then you keep moving the points except the intercepts. Now, let's look at the last thing here, the combination of functions. The combination of functions, I'm just going to list 2 or 3 things that I want you to have a look at. If 1, 2, okay. If f of x, right, has a domain d of f, and g of x has domain g of x, not g of x now, this time around I am going to say has domain d of g, right? Then remember that sometimes you have to split a domain and look into little pieces. That's what I want to emphasize here. Then the domain of g plus or minus f, right? If I were to add this function and that function, the domain of this is going to be x is an element of real numbers. That's the first thing, such that x is an element of df and x must be in g. So basically here you have this domain of f, we have that domain of g of x. So if we want the domain of f of x plus g of x, or g of x minus f of x, or f of x minus g of x, you want to take the intersection of this domain, the common domain between these two domains. So you want to take the intersection. That's the meaning of AND. So you want the intersection of these two domains. And if you want the domain of f of x divided by g of x, again, x is an element of real numbers such that x is an element of d of f and d of g, such that g of x is not equal to 0. So this is also another way of looking into this. If you, let's say, you end up having to add these two, or you divide these two, you get that. But if you are looking for the domain of f of x times g of x, the domain of f of x times g of x, x is an element of real numbers such that x is an element of d of f and d of g of x. So the domain of the addition and subtraction and the domain of multiplication is the same. So that's how you end up breaking down a very big function. For instance, if let's say I were to say find the domain of f of x is equal to, I want to say the square root of x squared plus the square root of 2 to the power x all over x squared plus 1. So because we have addition here, subtraction, and all these things, it's enough for you to find the domain of either the domain of this and the domain of that, the domain of or the domain of the numerator, the domain of the denominator, and then you find the intersection of these two domains such that this is not equal to 0. Of course, I am just specifying this so that when you're dealing with multiple choice questions, you know that this is something that does exist. I know that you already know how to calculate a domain if you are given a specified function, but these are extra rules that you can use, which are a shortcut. In a nutshell, the domain of f of x plus or minus g of x, it is the same as that. The domain of f of x divided by g of x, it is that. And the domain of f of x times g of x, it is equal to that. Thank you for taking a look at this particular lesson, and make sure that you look into the slides and see how the pictures look like. They look nicer there than when I was trying to draw them here. Look at the slides, read everything, and you can combine with this. And of course, if you feel like there's something that you don't understand, there will be a tutorial today that I will upload before 12, and also after I've uploaded your assignment, memorandum of assignment 1, so that you can know how you did in your previous assignment, so that you take the next assignment very seriously depending on what you have seen. So thank you for taking your time in actually learning this.